Alright, this is lab 4 and we're going to be going over circuits in this lab. So our purpose is to predict how circuits interact with each other in series and parallel resistors, as well as looking at the potential voltage differences between circuits at different locations and studying the behavior of resistors and capacitors and how they affect circuits. So the main fundamental principles we're going to be looking at are these three. This is going to be Loops rule, Node's rule, and Ohm's law, which are going to be looking at the voltage, the resistors, and the currents. So in our first problem, what you really need to look at is that both batteries are going to have 1.5 volts, so that means that you're going to have a total of 3 volts. And we're going to be looking at Ohm's law to calculate this. Ohm's law is the velocity equals the current times the resistors, and because this is a series, you're going to be adding up the two resistors to get a total of 147, and then from there you can do simple mathematics to know that each observed ammeter is going to be having a current of 0.02 amps. And you can see this setup right here. So some observations that we have from this setup is if you reverse your ammeter, there's no change. It's still going to be, the reading's going to stay the same. If you replace your ammeter with a voltmeter, it's going to be recording the volts instead of the ammeter. And what it's going to be recording is that there's 0 volts there. That's because there's no difference. It's going a steady state through the circuit, so there's going to be a 0 net difference. And during this, the other ammeter of the two is still going to record 0.2 amps. And the reason why is because the voltmeter does not, it has a very high resistor, and so none of the current goes through it, and so none of the voltage or the resistors really change in the current when this happens. And then when we measure the voltage at different locations, we can see that it's going to be 0 at the battery and the ammeter. However, it is going to be negative 0.959 volts and negative 2.047 volts at these two resistors, and that's because when you look at Loops rule, the V total, so when you add these two resistors up, it's going to have to cancel out with the amount of voltage at the beginning, which was 3, and so when you add these together, it's going to be a negative 3 plus a 3, which is going to equal 0. And so here we have a graph showing the voltage and how it's changing from each section of the as the current is moving through and passing through these resistors and amperators areas. So here's some questions. So if you run an amp meter parallel to a resistor, the amps that are in the currents actually increase because an amp meter itself doesn't have like a resistor in it, or it's a lot less than what would be in a 100 ohm resistor. And so the current is going to flow away from the resistor to the path of least resistance, basically. And that's going to increase the amps because you basically have less resistance when you're calculating like your Ohm's law. The resistance calculation values are right here to show how we calculated it, or how you get the values for each resistor at the wire and the amp meter. So now we're going to go into circuits and looking at bulbs. When you connect the bulb to a battery and there's a capacitor, the bulb is going to start off bright and then it's going to dim to nothing. The same happens when the bulb is connected to a charged capacitor. It's going to start off bright and it's going to dim to nothing. when the current goes through a capacitor, the currents are going to they're going to start off high and they're going to steadily decrease to 0. And when we did this experiment and I was seeing how long it took to charge or discharge a capacitor, when there was 10 ohms of light, it took 8.64 seconds, and when there was 20 ohms of light, it took 14.4 seconds. And here we can see our data when we calculated the voltage of the light versus the time, and then we linearized it so that we could find out the RC because the RC would tell us the I value, and so our slope linearized was negative 0.168, which the RC value would then be 5.95 because RC is negative 1 divided by the slope linearized value. And then you can compare that to the actual value for RC, which would be R, which is your 30 ohms, times it by the C, which is which is 0.2, and that would give you an RC value of 6. So our graphical RC value is not too far away from your calculated value. The measured time, it would be different from the predicted time, just simply due to the fact that there's going to be resistance and everything. Even if you don't have a resistor in the circuit, you will have resistance in wires and such.